Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome. My name is Bara Muhammad, and in this video, I'll walk you through our innovative temperature alert system project. This was a collaborative effort with my teammates Nuruddin Ahmed and Ahmed Shokri, where we designed a system to monitor, regulate, and alert users about unsafe temperature conditions in sensitive environments. In environments like server rooms, industrial processes, or homes, maintaining the right temperature is crucial. Extreme heat or cold can damage equipment, reduce efficiency, or cause discomfort. To solve this, we needed an automatic system that monitors temperature, controls heating or cooling, and warns users about unsafe conditions, all without constant supervision. Our solution is the temperature alert system, which uses combinational logic circuitry to ensure safety and efficiency. Let's know about our inputs and outputs. Starting with inputs, there are four inputs which are H, that is high temperature sensor, which detects if it's too hot. L, that is low temperature sensor, which detects if it's too cold. T, that is threshold indicator, which shows if the temperature is in the safe range. S, that is system on or off switch, which turns the system on or off. Also, there are four outputs, which are C, that is cooling, which turns on cooling when it's too hot. HT, that is heating, which turns on heating when it's too cold. E, that is error, which activates when both sensors activate. R, that is reset, which resets the system after fixing any errors. Now we will start with the steps to know how to draw our circuit diagram in Quartz. In this truth table, the input is, which is the on and off switch when it becomes 0 off the cooling. Heating and error output should be 0 since the AC is off, but the reset output will be on to reset it back to its natural state. If any of the other inputs like high temperature sensor or low temperature sensor or threshold indicator are on, but the switch is still off, then none of the output will be activated except reset output to reset it back to its natural state. Since the AC is off, so nothing is happening in the AC. When the switch is activated and the threshold input is activated, still none of the outputs won't activate since the AC is at normal temperature. When the switch is activated and the low temperature sensor input is activated, the low temperature sensor detects a very low temperature so that where the heating output begins to activate to increase the temperature. When the switch is activated and both the low temperature sensor and the threshold input activates, none of the output will be activated since the temperature is within the threshold. When the switch is activated and the high temperature sensor is activated, the high temperature sensor detects a very high temperature so that where the cooling output begins to activate to lower the temperature. When the switch is activated and both the high temperature sensor and the threshold input activates, none of the output will activate since the temperature is within the threshold. When the switch is activated and both the high and low temperature sensor is activated, it will result in both the heating and cooling output to activate, which will cause the error output to also activate. That means there is an error in the AC itself. When the switch is activated and all of the other inputs are activated, none of the outputs will activate since the threshold input is activated, so the temperature is within the threshold. Next step, In the K-map, we have to use the input and outputs for the truth table we made to make the K-map for the 4 outputs. This K-map is for the output R, which is the reset output. So, in the inputs 0000, 0001, 0010, 0011, 0100, 0101, 0110, and 0111. The output will be 1. So using the K-map rules, we have to always circle the outputs 1. We cannot circle 0, and we have to circle powers of 2. For example, if we have 2 outputs of 1, we can circle them. If we have 3, we cannot circle 3 since it is not a power of 2. So we have to circle 2 outputs of 1 and the other 2 outputs of 1. So here in the K-map, we have 8 outputs of 1, which is power of 2. So we circle it to get the Boolean equation from it. We have to see the column 0, 0 and 0, 1, where the S is 0 in both columns, but H is 0 in 0, 0, and in 0, 1, it is 1. So we can't put H in the Boolean equation since they are different in both column, but we can put S since they are both the same in both column, but it will be S bar. Since it's 0 in both columns, if it was 1 in both columns, then it will be S only. So the equation for R is R equal S bar. In the K-map of HT, there is only 2 outputs of 1, which is in 1110 and 1010. So since they are a power of 2, then find the Boolean equation. In both columns 1, 1 and 1, 0. The S is 1 in both columns, but the H is 1 and 0 in both columns. So we won't put in the equation. And in the row, the L is 1 and T is 0. So T will be T bar since it's 0. So the equation will be HT equal SLT bar. In the K-map for C, there is only 2 outputs of 1, but separated from each other in 1100 and 1110. So there is one column where S and H is 1, but in both rows, L is different in both rows, so it won't be in the equation, but T is the same in both rows, but it is 0. So it will be T bar. So the equation will be C equal SHT bar. In the K-map for output E, there is only one output of 1, which is at 1110. So in the column, the S and H is 1. So it will be SH, and in the row, the L is 1 and it is 0. So it will be LT bar. So the equation will be E equal SHLT bar.
In this part, we are going to demonstrate how to configure the basic gate configuration using a Quartus 2 program. And so we are firstly going to open a new project wizard so that we can create our own directory for the outputs and also the simulation files. For this file, we are going to name it temperature underscore sensor underscore basic, since we'll be using only basic gates for this configuration. Then we're going to proceed to click on new and then select block diagram slash schematic file. And this is the interface that we will be using to create our combinational logic circuit. Our first step is going to be listing down all of the inputs and also all of the outputs. So the input from top to bottom will be S, H, L, and T, while the outputs are going to be R, H, T, C, and E. These are arranged according to MSB and LSB. Based on the Boolean expression for each output, done by simplification of K-map, we can know what type of gate to be used in the combinational logic circuit design. So in this case, we'll be using AND gate and also a NOT gate. Since we know from the Boolean expression that for HT the input will be SLT bar, we must use a 3-input AND gate, and we just connect all of the required connections. This process is then repeated for all of the outputs according to their respective Boolean expressions. So for the last output, which is E, it's going to accept 4 inputs. So we'll be using a 4-input AND gate. After making all of the required connections, we must run a compilation so that we know our circuit is running properly. And in this case, it reads successful, which means our circuit is complete. After that, we are going to click on New and then University Program VWF. And this will bring you to an interface which is required for us to read the waveform produced. After that, we are going to click on Edit and Insert Node, and then we're going to click on Node Finder. And by clicking on List, we are going to list all of the respective input and outputs that are contained within our combinational logic circuit. And finally, we adjust the input value either 1 or 0 according to our desired value, and the output should produce according to our truth table. And in this case, yes, every result produced is according to the truth table, and we know that this circuit is correct. This part, we're going to demonstrate how you are going to build the circuit using only universal gates, which in our case, we're going to be using only NAND gates. And first off, we're going to start by putting all of the inputs and all of the outputs and labeling them according to their respective MSB and LSB bits. For the top part, we have the MSB bits, and for the bottom part, we have the LSB bits. In this part, we'll be using 5 2-input NAND gates, 2 3-input NAND gates, and 1 4-input NAND gate. And we just connect them respectively to our desired inputs. So for the R output, it's just going to be a NOT gate, and in the universal gates, we just be using a 2-input NAND gate. We put 3-input NAND gates and also a 4-input NAND gate so that it can replicate the same output as using only one AND gate, because we're using only universal gates in this circuit. After making all of the connection, we should run the compilation so that we know our program can run successfully. And in this case, thankfully, it can run. And after saving the file, we must proceed to creating the waveform file. We should expect the same result pattern as if we are using only basic gates, because we are only changing the type of gates that we used. And as you can see, the results all fulfill our truth table and also Boolean expression.
Finally, this temperature alert system uses smart automation to manage temperature-sensitive tasks easily and safely. Its efficient design ensures reliable operation while reducing risks and effort. Big thanks to my teammates, Nuruddin Ahmed and Ahmed Shukri, for their contributions. See you next time.